Okay, we are ready to start the tutorial for topic 12, first law of thermodynamics. Okay, there are a total of 10 questions in section B. So what we will do is that we'll break it up into two sections, two separate recordings, and I'll put click points for you in the video itself so you can jump to the question that you want. So I think in YouTube there's a way to set the chapters. So we use that to make it easier for you to jump between questions. Alright, so I hope you have already completed the lecture series and then you are here because you have already tried the questions and you just need a bit of clarification for how the steps are done. Okay, so this is what we will do for you. Alright, so let's go through this one. Alright, so okay, I'm going to be writing, so to bear in mind the bad handwriting just in case. Okay, let's look at the first question for section B, question 1. Okay, first question, you have an electric kettle that's rated at 1.5 kilowatts. It has a heat capacity of 840 joules per Kelvin and contains 1.7 kg of water, which you are given the specific heat cap. Okay, so take note of the values are given. You are given heat capacity and then you are given specific heat cap. Alright, so remember heat capacity does not take into account it takes into account the mass as well. Right, if a kettle takes 435 seconds to warm up from 10 degrees Celsius to 90 degrees Celsius, calculate the total energy received by the kettle and the water. Alright, so this one you need to count in both types of energy. Let's just use black pen. Okay, so let's make it a little bit bigger. Alright, so we need to do total Q in. Okay, Q in will consist of Q to kettle and then plus the Q supplied to water. Okay, so Q supplied to kettle is just 840 joules. So this is, you just need to take the heat capacity 840 multiplied by change in temperature of 90 minus 10 and then plus mass of the water, which is 1.7 kg, times heat capacity of water, which is 4.2 times 10 power 3, and then 90 minus 10 again, and then your final answer is 6.38 times 10 power 5 joules, right? So that's part 1. Okay, next you're asked to work out the amount of heat lost to the surroundings. Okay, so heat lost to the surroundings, basically you have, if you write it out again, so you have Q supplied from the heater, Q in, okay, is used to do two things. This is divided into useful and then Q heat loss. Okay, so this value here, the one they've calculated on top, this one is a Q useful. Okay, because this is the one that's used to do useful work. Alright, so how to find Q in? Q in, because we have the power of the kettle, we also have the time it takes. So we can just do we can just take 1500 watts multiplied by 435 seconds equals to Q useful 6.38 times 10 power 5 plus Q loss. Okay, and this will give you Q loss of 1.41 times 10 power 4 joules. Right? So this is a nice question to warm up with. It's very straightforward. Yep. So nothing too complicated for this one. Alright, let's move on to question 2. Okay, question 2, again, you're doing a heating experiment. Energy is supplied at a constant rate to a liquid in a beaker of negligible heat capacity. Right, so basically the beaker is essentially does not need any energy to increase in temperature. Okay, the temperature of the liquid rises at 4 Kelvin per minute just before it begins to boil. It takes 40 minutes to boil away all the liquid. For this liquid, calculate the ratio of specific heat cap to specific latent heat of vaporization. Leave your answer to 3SF in units of K -1. Okay, so this is a heater. The heater is used to do two things, right? The heater is used to first, so whatever energy is supplied, so let's just write Q supply. Q supply is used to do two things. Q, rise in temperature, and then plus Q used for boiling. Okay, but the power is the same. So this power supplied is equals to the power that's used to rise the temperature plus the power used for boiling. Alright, so we can write it in an easy way. So if we look at this one here, what we can do is that if we take this expression here, we write this out. Okay, so the power to rise temperature is essentially mc delta theta divided by time. Then the power to do the boiling is just mLV divided by time. Of course, the timing is different, so let's just write the timing there. Okay, then since the mass is the same, we can make some cancellations first. We can cancel away m, of course. And then we're left with c delta theta and then the LV. Okay. So what else do we need? Let's see. 4 kelvins per minute. Okay, so we are given the rise in temperature 4 Kelvin per minute. Alright. So we can just leave the timing in terms of minutes, it's fine. So we have this C delta T. Let's write next line first. So you have C, and then you have this delta theta over time. Let me just circle this expression here, over here. Alright. So this is basically your 4. Okay, so this one you can write in as 4.0. Okay, and this is equals to LV over T2. Okay, let's go back to the other color. Let's go back to the other color. Okay, so LV is, we don't know LV, so we just write LV here. And then we have T2. T2 is how long? 40 minutes, so just write 40 here. Alright, and then if you rearrange this, okay, you should get to this point where you have C over LV is equals to 6.25 times 10 negative 3 per Kelvin. Okay, so if you look at the answer key, right, I actually wrote in to convert back to 60 as in divide, convert to seconds. But the cancellations, the 60 will have cancelled off. So if let's say I write 60 over here, right, this one over here will be divided by 60, and then this one here also will be divided by 60. Okay, so 60, right? So you will cancel cancel each other off. So there's no need to write, right? Because you know that you're going to divide both sides by the same units in time, so it doesn't really matter lah. Okay, let's move on. Question 3. Okay, this one is a bit more interesting. You have two spheres, both made of steel. Sphere P has a radius that's larger than that of Q. Initially, P is a temperature Tp and Q is a temperature Tq, where Tp is larger than Tq. Spheres are brought into contact, and their final temperature is T. No thermal energy is transferred from the spheres to the surroundings. Which expression gives a relationship between Tp, Tq, and Te? Okay, for this, you know that at the end, these two spheres will settle at the same temperature. Okay, so the final temperature is T. Okay, so you can see that the change in temperature for P, this will be from Tp to T. And then the gain, so this is a loss in temperature obviously because Tp is higher than Tq. And then for Q, this will be from T minus Tq. Okay, so because they have the same substance, so basically they have the same heat capacity. Okay, let's just solve it here on the spot. I think we have more space here. Okay, so let's write this out. Since there's no heat loss to surroundings, that makes our life a little bit easier. We know that the Q loss by P is equal to the Q gain by Q. Okay, okay, there are two Qs. I should put sphere Q and sphere P to avoid confusion. Okay, so then we can write the equation. So the energy lost by P is just using the specific heat cap. So we can take mass of P times heat capacity, and this is Tp minus T. And then this side here will be M Q C T minus TQ. Okay. Right, so let's look at what we are supposed to find first. Let's just scroll down and look at this. So we're trying to find the relationship between TP minus T and T minus TQ. Okay, so with that in mind, let's continue. Okay, then we can see that, we can strike off the masses. We can strike off the heat capacity. Okay, so let's strike it off first. Heat capacity is gone. Okay, we're left with MP and MQ. Okay, I'm going to rearrange to make to shift all the T's to one side first. So what I'll do is I will shift the T's to the left hand side and the Q's to the right hand side. So this will become TP minus T, T minus TQ equals to MQ over MP. Okay, MQ over MP, we can further expand it, right? Actually, is there a need to expand this? Okay, I will just, you can see that basically P, if they're made of the same material, right, P will have a larger mass. So if P has a larger mass, that means this ratio here is less than 1. Okay, if it's less than 1, that means over here, continue the side here, if I take this form compared to this one here, I can say that Tp minus T is, I can therefore conclude that Tp minus T is less than T minus TQ. Okay, and the answer here should be C. Am I correct? Yeah, it's correct. Okay, if you want to, right, you can actually further break up this MQ to MQ and MP to in terms of the radius. But since both of them are the same shape and it's just down to radius, right, then you can basically know that P will have a larger mass. Okay, so that's question 3. All right, no need to, if you want to, you can break down into, like, let me just do for your side lah. So you know that your mass of a sphere is essentially this density multiplied by volume. Volume of sphere is just equals to 4 third pi r cube. Okay, and then you can make the necessary cancellation. So you realize that the ratio of MP to MQ is just RP cube RQ cube. Okay, so you can do that if you want to. Okay, but otherwise there's no real need to do so. Okay, because it's the same shape. All right. So this is question 3. Question 4. Okay, question 4. Question 4, you have a calorimeter of mass 125 grams that contains 130 grams of water at 25 degrees Celsius. Some steam at 100 degrees Celsius was introduced into the calorimeter and was condensed into water. Final temperature of the system is 48 degrees Celsius. Assuming no heat loss to the surroundings, calculate the mass of steam that was introduced. Okay, so basically you have a calorimeter. Let me just try to draw something. So you have a calorimeter with mass. So this is this calorimeter and then you have some water. Okay, what you do is that this is originally at 25 degrees Celsius. Then you add in some steam at 100 degrees Celsius. Then together the conclusion is you have your calorimeter plus water plus extra water from the steam, and this is at 48 degrees Celsius. Okay, so this is what you are doing. Okay, so basically whatever heat, then since there's no heat loss to the surroundings, that makes it very easy to do. Okay, you just need to write out what is the heat, what's the energy Q loss by steam equals to the Q gain by original water and calorimeter. Okay, so heat loss by steam needs to condense first, so this is MLV plus MC delta theta. Delta is from 100 to 48, so 100 minus 48. okay, equals to, do we have the heat capacity of the calorimeter we have? Okay, so this one will be m of the calorimeter, m of the calorimeter first, so 0.125 times 900. Okay, since we can put the change in temperature outside because it's the same, then we do for water, so 4.2 times 10 power 3, then let me write it at the bottom, 0.130. Okay, then this whole thing multiply by 48 minus 25. Okay, so if you do it this way, right, then you can just solve very quickly. Okay, then you sub in the values for LV lah. LV I think is 2.26 times 10 power 6. Then C for the water. Now because now your steam will have condensed water first over here, so this is for condensation. After this, your hot water at 100 degrees Celsius needs to go down to 48 degrees Celsius. Okay, so I'm just supposed to find M here. And once you found M, you work this out, you get 6.11 grams. Okay. Yep. So I don't think there's a need to go into so much detail for this question here. I think it's quite direct. Okay. Next, let's look at question 5. Question 5 is quite long. Some of the things I won't go through because they're in the notes. Okay, so you have an experiment to determine the specific latent heat of vaporization of a liquid. A student obtained two sets of readings using electrical heating method. V and I, the potential difference maintained across, and the current through the heating coil respectively. The liquid was maintained at its boiling point by the heating coil. Okay, so you are given V and I. You can find the power. So I hope you remember how to find that. It's just power is equals to V times I, right? Okay, next then you're asked to define the specific latent heat of vaporization and specific latent heat of fusion. So if you go to your notes, your vaporization is defined as the amount of heat that must be supplied to it to cause a unit mass of the body to undergo a phase change from liquid to vapor. Then fusion is the same thing as well. Okay, then you're asked to explain using a kinetic model why the specific latent heat of vaporization is greater than the specific latent heat of fusion for the same liquid. Okay, essentially what's happening here is that when you want to go from a solid to liquid, right? Your solid masses, your solid molecules are very close to each other. Okay, a liquid is a little more spaced out. Okay, but a gas is much more spaced out. Okay, I think I need to draw it more spaced out. Hold on. Erase this one first. Okay, so let's draw this a little bit more space out. Okay, so when you go from solid to liquid, right, you don't need to push out against the atmosphere so much. Okay, remember it's the surrounding, you have the atmosphere. The atmosphere is applying atmospheric pressure on your substance. Okay, so there's atmospheric pressure from all around. Okay, when you're changing from solid to liquid, right, the expansion is not very much. So there's not much work done against the surroundings. Okay, but if you go from liquid to gas, you see that this expansion is much bigger. So more work has been done against the atmosphere. You need to supply energy to do this amount of work. Second thing, you remember that your potential energy of your molecules is inversely proportional to the distance between them. The closer the molecules are together, the lower PE they have. Okay, so if you want to go from liquid to solid to liquid, right, the change in separation is not so high compared to liquid to gas. So your liquid to gas has to gain much more PE than from solid to liquid. Okay, so that explains this part. You can check your notes for this section. You can go and rewatch the video as well if you need to. Okay, why do you need two sets of readings? I think this one we explore inside your lecture notes and so the lecture video. Basically, there's heat loss to the surroundings. Okay, you need to do two different sets of readings. Okay, so what's happening here is that, let me backtrack a bit. Each of these readings, right, will give you a certain amount of power. Alright, so let's just quickly work out power. 150 times 2.5 that is how much? 75 times 150 times 2.5. 300, 400, 375, right? I think 375 watts. Oops. 375 watts. Okay, then this one 111 times 2 1. Easy to work. 222 watts. Okay. In this 2 power here, right? There's some energy loss. Okay. The energy loss, because the heat loss is at the constant, because the temperature is the same, your room temperature is the same, right? The heat loss takes place at the constant rate. Okay. So that H over T is a constant rate. So you need to use 2 readings to go and calculate what's the heat loss. Okay. So basically the idea is that I can write 2 equations, right? Then later I can just subtract them. Okay, to find the heat loss. Okay, so you're asked to work out what's the specific latent heat of vaporization of the liquid. Then after that, calculate the amount of heat supplied that was not used to vaporize the liquid in each experiment. Okay, so let's look at this one. Okay, we need to write 2 equations first. Okay, so first one, let's do for experiment 1 first. So P1. So experiment 1, let's write it first. Experiment 1. Okay, I can do P1T, P1T1 equals to, is used to do boiling and used to for heat loss. So this is M1 LV plus H. Okay, sub in the values. Okay, in fact we can do some rearrangement first. I'll just follow the one in my notes so it's easier for you to go along with it. Okay, so what I can do is I'll divide everything by T1. So I do P1 equals to M1 LV T1 plus H over T1. Alright, so this is the first equation. Okay, then after this you can do the same for second one. So maybe use red color here. Second one will be P2T2 equals to M2 LV plus H. Okay, so P2 is equals to M2 LV over T2 plus H over T2. Okay, so what we can do now, we can just subtract them. Okay, because I know P1 and P2. P1 and P2 I can obtain from my V and I. Okay, so let's try this. So let's just do, and we can see that clearly 1 is larger than 2 to the power. So let's just use P1 minus P2. Okay, so let's do it this way. So let's do 1. We can do 1 minus 8. Why is it not coming out? Yeah, some tech problems. Let me pause this first. Okay, sorry for a delay. Yeah, you won't see the delay because I paused it. Okay, so I'll take 1 minus 2. So this is equation 1 minus equation 2. So I will get P1 minus P2. Okay, so I'll take P1 minus P2. Okay, and this is equals to M1 LV T1 plus H over T1 minus M2 LV over T2 minus H over T2. Okay. Okay, since the heat loss is the same in both cases, basically this H over T1 and H over T2, they're the same value. So you can cancel each of them off. Okay, so then you are left with just, okay, we can start to sub in the, okay, maybe you write one more line before summing the value. So P1 minus P2 equals to M1 LV T1 minus M2 LV over T2. Alright, so let's try to sub in the values now. P1 is 150, 2.5, 110, 2.0. So this will be 150 times 2.5 minus 111 times 2.0 equals to, do we have the masses? We have the masses, and do we have the timing? We have the timing. Wait, the timing. Wait. Oh, 20 minutes. Okay, so yep. So this one is 478 grams and 264 grams. Okay. So basically, I can take out LV. LV, I put it over here. So this is 0.478 over 1,200. Oops, sorry, extra 0. Okay, minus away 264 grams. Okay, so 0.264 over the same 1,200. Okay, if you do it this way, you get LV to be equals to 8.58 times 10 power 5 joules per kg. Alright, then next you are asked to find the heat loss in which part? You are supposed to find the amount of heat that was not used to vaporize the liquid in each experiment. So you need to do both. Okay, do I need to do both? Let's see. Sub equation 3 to equation 1. Okay, so once I work out LV, I can go in to go and solve for this one. Okay, I just need to sub LV into equation 1 or 3 lah. So let's just do this. Okay, so let's do sub LV equals to 8.58 times 10 power 5 into equation 1. So that will give me 150 2.5 equals to 8.58 times 10 power 5 over 0.478 divided by 1002 plus H over T T1. Okay, yeah, the timing is the same, so you can, that's why previously you can strike off you can strike off these two terms. Both are over 1200 seconds. Okay, so once you have this, you rearrange this equation. You have H over T1 equals to 33.2 watts. Just rearrange this one lah. Okay, so H will just be equals to 33.2 multiplied by 1200. This will give you 39800 watts. Okay, this is still 3SF. Right, so this is it for tutorial 1 of this chapter. Okay, so please go and try the questions if you have not done so. Yep, then after this, go and try the next set of questions, 6, 7, 8, 9, 10. Then come back to watch the next set of videos. Right.